Hello, my name is Rafael, and I'm going to present our work entitled Concept Drift Detection and Localization in Process Mining. This work was done by Dr. Pérez, Dr. Fantinato, and me from University of São Paulo, and Dr. Hargers from Utrecht University. We will start by going through the context of this work, then some literature review with correlated work. Then I will detail our approach, and finally we have some final considerations. So starting with context, I will show you our motivation, our goals, and how we aim to tackle. So nowadays, the organizations have to deal with several situations on their day-to-day life, like changes in legislation, economics, or, as we have seen recently, a pandemic. These changes affect their business process, and they are usually not structured properly and not well documented. So being able to detect and understand those changes can provide a competitive edge for organizations. Inside that context, our goal is to develop an approach that performs online concept drift detection and localization in business process. So what would be a concept drift in a business process? For example, we have process model here, and before timestamp TC, the process model starts at A, then has a conditional gate here, either B or C, then D, right? So after the timestamp TC here, process model, the conditional gate is gone, and now it's only a sequence of A, B, C, and D. And we can say here that we have a drift at timestamp TC because the process behavior has changed before this time. So our goal here is to develop an approach that can do the detection, that indicates how to detect the points in time when the drift occurs. So let's say we identify that it occurred at TC, and the localization. In localization, here we will identify the entities involved in the drift. So in this case, we have B and C here as the activities that are involved in the drift. Our idea is to perform both tasks together, right? Now let me show you how we approach this problem. Here we have a process model and its traces. They identify an instance of execution of this process, so it has executions starting here, going here, or going this way. So there are many executions at the same process, right? So as they are occurring, they are also being logged in an event log that register the execution of each activity, right? And in process mining, we aim to extract value from this event log, so we don't necessarily need the process model here. We only look at the event log, right? And we are also going to do that. And here, what we are going to do with the event log. So we will apply clustering algorithm over the traces in consecutive windows. So we separate the event log here in windows, and for each window, we apply clustering algorithm, right? In this example here, we have cluster 1 here, that's the red path, and cluster 2 is the greenish path here, right? And the first two windows, the clustering remains stable, but at the third window, the clustering changes a lot because the first group actually is closer to the second group now, because it looks like this red behavior is not occurring anymore. So we can say that there is a drift here because the process behavior has changed. So we suggest that we can capture changes in process behavior by capturing changes in trace clustering, right? So when we have a significant change here, we suggest that a drift has been found. Okay. Now we will go over some correlated work that tackles the drift detection and localization process mining. And drift detection methods, they are usually based on comparing traces in consecutive windows to decide whether significant difference has been found, and if they are significant enough to be considered as a drift. We divide them into groups, the ones based on similarity, where features are extracted from the event logs to be compared, and the other ones based on statistical testing over frequency. In our work would be in the similarity group, right? And drift localization methods are usually based on comparing the process behavior before and after the drift. We divide the approaches into three groups. One that's based on similarity, where they have the process model reference or they use process discovery techniques, and the other group is the one that uses statistical tests over some specific feature of the process. And the last method, they are based on representing the process behavior in other structures, such as graphs or trees. Okay, and we can see from that only two approaches they deal with the two tasks. They do both detection and localization of drift, and the localization usually requires additional data, additional structure, or a reference from the process model, and that increases complexity a lot. So what we want here is to do both tasks without the requirement of additional data or model reference. Okay. Now I will go over our approach, presenting first an overview, and I'm going to detail and present the experiments we have run. Okay. This is what our method looks like from left to right, like a pipeline. So first we have the event log here. That is our input. We perform our windowing model here. So we take the event log and take the first traces as a window, then the consecutive traces as the other window. And to use the clustering algorithm, we first need to represent traces in a vector space, right? So it can be done based on the activities and the transitions that are occurring in the trace, and we can count the occurrence or we can count the frequency of those activities or transitions in the trace. So after we have the traces in a vector space here, we perform the clustering. In this case, we're going to use the k-means plus algorithm. And after we have the clusters, we can perform the drift detection. So our method is going to look at the evolution of clusterings. So we extract features for each clustering, and we look at how they evolve over time. And based on a rolling standard deviation tolerance, we see if there's a significant change there to detect a drift. When a drift is detected, we also perform the drift localization. That's based on calculating the mean square error of the centroid's dimensions before and after the drift. So we can see what dimension is impacting more in the drift. And to evaluate this process, we have the F-score to identify how well we are detecting drift, if we're not having a lot of false negatives or false positives. And we also have the mean delay to see how long does it take for our method to detect the drift after it is happened. And we have the area under the rock curve to calculate how our localization is really selecting only the activities involved in the drift. Okay. And as an example of trace vector representations, we have here this baseline process and two variations, A and B. Okay. We have also three examples of traces, each one from each process. So we have ABD here for baseline, and DBA, where we switch the order here of A and D, and B, that is 3 A's and in a loop here that we add, and B and D. Okay. The activity occurrence representation does not distinguish over loops or order. It just counts the occurrence of each activity. So all of them, all the drift and traces, they are the same here in this vector representation. The frequency representation distinguishes loops, so it counts when the activity occurs more than once. Here we have 3, but does not distinguish the order. So ABG and DBA, they are the same here in this representation. And the transitions representation, it requires more dimensions, right? Because we have one for each possible transition. But it's able to represent loops and changes in orders. So all these three traces, they are different here in the transitions schema. So that's what each representation has its characteristics, right? So to illustrate our approach, in here we have a trace stream right here, and the first step we do is to obtain a window of traces in a vector space that we can cluster, right? So we then perform trace vector representation for each trace. Then we have a window. In this case, we have two windows here. Each one gives us 3 clusters, right? With this, we can perform the drift detection. So for each window, we calculate some feature here. In this case, we're calculating the distance between the centroids, right? So that is the intercluster distance, and we evaluate how it changes over time. We can see here that at window 2, there's a sudden decrease here in the feature that indicates a possible drift here. So our method identifies a drift here because all the clusters now, they are more together, they are closer to each other than they were at the first window. Okay. In the drift localization, we have a drift detect at some point in time, and we take the window before and the window after. We compare the centroids here, calculating the mean squared error for each dimension, and we get where it has changed more now. Okay. So for the experiment setup, we have a set of event logs based on the low applications process model with synthetic concept drift. So this is the process model of the low applications that we have used. It has 15 activities, 1 parallel gate, and 4 conditional gates here. And it has 3 exits and 1 start point. Right? So this is the base model. And to generate concept drift, they produce different process variants. So they have one baseline process, the one that I showed you before, and they add something different, and they merge the event logs of the baseline process and of the process variant. And this event log merge, it has 9 concept drifts, right? So it has one from baseline, one from the process variant, one from baseline, and so on. Okay. This was done in the full data set. We have 12 different process variants, and each one changes a different aspect of the process, right? So one make fragments skippable, the other one synchronizes 2 fragments, makes 2 fragments conditional, and so on. Also, the activity-based representations, they are not able to distinguish all possible changes in those processes, right? So we show them in the table here as a dash. The X marks the representation that is able to support those kind of changes. Okay. And for the experiment, we have set up a set of parameters. So we consider different features for clustering evolution. So we take here intercluster distance. We have some cluster validation index here. We have the mean squared error also, and some aggregations, different aggregations here. And for the algorithms, we have also a set of parameters. So we change the trace vector representation, we change the size of the window, right? And the number of clusters, and the parameters that adjust the sensitiveness of our method, sensibility of our method. Okay. Now this is an example of execution of our approach for a specific event log with these parameters we describe here. And in here we can see that the red line, it describes the feature value over time, so the feature that we analyze the clustering evolution. And the green line, it represents the rolling mean, okay? And the vertical lines represents the drift. The green vertical line represents the true concept drift, and the yellow vertical line represents the detected concept drift. The blue areas are the tolerance boundaries we calculate each step. So zooming in here, we can see that right after a drift has occurred, for example here at trace index 3000, we can see that the feature value drops a lot and changes very dramatically here. And we can see that's right exactly where a drift has occurred. So when a drift occurs, it goes down, and it becomes stable for until the next drift. So when the next drift occurs, it goes up again, and we can see that every time this happens, we can detect a drift, right? So we can see that the tolerance up here, we expected a value inside this blue area right here, somewhere around here, but the actual value was here. So That's why our method could detect a drift here, and that's the yellow dashed line here. In this example, we have found 9 out of 9 drifts with no false positives. Okay. So this is the result of the localization method for both a false positive drift and a true positive drift. We have selected here the top 10 activities. In the false positive scenario, we see here that some activities have really small mean squared error here, but when there's a true positive drift, the activities that are actually involved in the drift, they are these two here. They have a high score here in the mean squared error. Okay, so we can see how much they are involved in these changes in the drift. So these are the compiled best results for each representation in each process variant. Here we have considered the best combination of parameters for each trace vector representation. We can see that the transitions profile showed lower mean delays in general, but overall it had a worse F-score results when compared to the activity frequency here. And they all performed well with F-score higher than 0.9 in most cases, except for the variant FR here that has been very difficult for our method. And this variant it shows only a small variation in the process behavior, so it's very subtle. That's why it's hard to have the sensibility to detect it. So the only change that happens here in this variant is that when generating the event log for all the conditional changes, we have a 50% chance of going up or going down in a path, right? In this case, the variant increases that percentage of 80% for going one way and 20% of going one way in a conditional gate. So there is no changes in any of the traces, just the number of traces following a specific path. That's why it's such a subtle change, and it was hard for our method here in this scenario. Okay. Here we have compared our results to the baseline that was executed in the same condition as ours. With our best configuration of parameters here, our methods have performed better or equal in half the cases. However, when we consider the best configuration of parameters for each of the process variants here, individually, our method performed better or equally for all cases, including FR, which is the hardest one here. So this shows that better results can be obtained by our method if we adjust the parameters and drift sensibility according to the scenario we are analyzing. Okay. And here we have the results for the localization test. And the profiles based on activity, they have shown almost perfect score in all process variants they support, including FR. And the representation based on transitions profile did not perform as well. As it has more dimensions, the centroids are more naturally subject to fluctuations. Okay, and those natural fluctuations, they ended up affecting these results negatively. Okay. Now we will go over some final considerations to show our contributions, some limits of this work, and possible extensions. Here in this work we have presented a method that performs drift detection and localization together, using the same data structure we obtained with trace clustering, right? To create our vector space representation, we have assumed prior knowledge of all possible activities, which might not be the case in real-life scenario. Also, we are bound to limitations in trace vector representations and clustering algorithms. New avenues to extend this work include the usage of streaming clustering algorithms, adaptive window models, combination of different trace representations, and to perform experiments in real-world event logs. These are the references cited in this presentation, and they are also all present in the paper. Thank you.